We start with a picture of two vectors that we'll call V1 and V2. And we draw any vector on this board with its, we're going to assume that these vectors are drawn with their initial points at, say, the origin of a coordinate system or at some specified point. So let's say we have a third vector, and let's call this vector V. Now V can be expressed as a sum of two vectors in any number of ways, okay? I could take one vector, let's say here, let's call this vector W1. And I've indicated W1 being along the same line as V1, so that W1 is really a multiple of V1. And then another vector such that a W2 such that W1 plus W2 equals the V vector. Okay, well there's a W1 and here's a W2 and they add up to the V vector. Okay? And W1 is a multiple of V1. However, clearly W2 is not a multiple of V2 because any multiple of V2 has to be in the same direction as V2. Well, V2 is in this direction, W2 is in this direction. They aren't in the same direction. So it looks to me like I've got my subscripts wrong. Okay. This vector should have been V2. This vector should have been V1, so that my W1 should have been a W2, and my W2 should have been a W1, so that these statements are true. Okay? So again, I got a V1 and a V2 in a vector V. I take a multiple of this vector, which is now V2, and I call that multiple W2. And then I take a vector from the head of this vector to the head of the V vector, so that this vector plus this vector add up to the V vector. And this vector is my W2, this vector is my W1. Okay? Now, as I said before, using the reverse subscripts, W2 is a multiple of V2. Okay, so this statement is now true since I switched my subscripts. But W1 is not a multiple of V1 because W1's here and V1's in this direction. They're not quite in the same direction. It's not all that close. They're not all that nearly in the same direction. So we want to draw two vectors that do add up to V. Call the vectors U2 and U1, where U2 is a multiple of V2 and U1 is a multiple of V1. So we want multiples of V1 and V2 that add up to V. Okay, how are we going to make that happen? Well, the problem with the W2 vector is that to get from the tip of the W2 vector to the tip of the V vector, we had to move in this direction, whereas V1 is in this direction. Okay, if we use a shorter multiple of W2, then we would move more in the direction of V2, so, or of V1. So what we want to do is maybe from the tip of V, we come back in the direction of V1 until we hit the V2 vector, and then we make a vector from here to here and call that U2, and a vector from here to here, which we could call U1. And now, U2 is a multiple of V2 because it's in the same direction as V2. And if we got the direction right when we came back from here to here, U1 will be in the direction of V1, so it'll be a multiple of V1. So now we have a U1 and a U2. U2 in the direction of W2, so it's a multiple of W2. U1 in the direction of V1, so it's a multiple of V1 that add up to the V vector. Now there's only, it turns out, exactly one way to do this. Now there are actually two ways on the picture that we could have gone about it. We could have come back from the tip of V in the direction, along a line parallel to the V2 vector, and we would have gotten our U1 here and our U2 here, but they would have been identical to the U1 and U2 that we got here. That takes some proof, but you can pretty easily prove that. Okay? Now, we made some estimates. And the estimates that we made were with a different picture, so they don't necessarily reflect what we have here. If we look at U1 and V1, we see that U1 is a little shorter than V1. Okay? So I would say that U1 being a little shorter than V1 is probably about 0.8 times V1. And U2, it actually looks more like 2/3 of V2, so I'm going to change my 3/4 to 2/3. So now we can say V, the vector V, is a linear combination C1 V1 plus C2 V2 with C1 now equal to 0.8 to match the picture. We had a perfectly good picture, but I wanted to construct a picture for you so you'd see kind of how it was going on. But C1 equals 0.8, C2 equals 2/3. Again, C2 V2 is 2/3 of V2. Here's V2, 2/3 V2, same direction as V2, 2/3 as long. Okay? C1 V1, C1 is 0.8, so here's V1. 8/10 of V1 is about this, and that matches the U1 vector, approximately. So we get the idea of how any vector that we want to draw on this board, or even imagine drawing if the board was infinitely big, in whatever direction, we can find a C1 and a C2 such that C1 V1 plus C2 V2 is equal to that vector. And incidentally, I mentioned if the vector was, let's say, here, then we would have to extend V2 backwards a little ways, and it'd have to actually go off the board here so that we could get back to it with a vector parallel to V2. So we'd have a negative multiple of V2. We get back to it with a multiple of V1, okay? This vector would have to be a negative multiple of V2 because we know that a negative multiple goes in the opposite direction, okay? So our two multiples would be like this, extending off the board, and like this, meeting this out at some point here, and there would be our multiple of V2 and our multiple of V1. So again, it should be clear that any vector we want to draw in the plane can be expressed as a linear combination of V1 and V2, as a sum of multiples of V1 and V2, and we can imagine that process geometrically, and it's actually a fairly simple process.